Well, good afternoon and welcome to TELUS Science Museum. I'm Dave Dundee. I'm Director of Education here, and I'm so glad you've decided to spend part of your day here at my favorite science museum. And like I always do, just wanted to tell you about some exciting things coming up. On August 17, we've got a fossil workshop here at the museum on that Saturday. And we still have some room left if you're interested in signing up for that. And for those of you who are 21 and older, we have a science comedy night. Yep, not you heard it here. Stand-up comedy. We have a troupe of scientists from Georgia Tech that do stand-up comedy, and we have tickets on sale for that for September 13th, that evening. And in the observatory on September 14th, we have the International Observe the Moon Night. And it'll be around a first quarter moon. It'll be really pretty, and hopefully the weather will be good, and you can get a great view of the moon. The next Lunch and Learn will be on September 25th. We will have a panel of experts up here at the front and talking about chasing the eclipse this past April, and talking about their adventures and some of the things, and we'll share some pictures of that. And also coming up in September, on the 24th of September, we've got an astronaut. Terry Virts, veteran astronaut, will be here giving a talk and also signing his new book. And we also have a NASA expert, and she will be here signing her book called Space Bites, because she's an expert in designing astronaut menus, and we'll be talking about that day. And that'll be on the 24th of September, rather of August, and we are selling tickets for that as well. And today's talk, we want to thank our sponsors, Marriott Courtyard of Cartersville, and also Century Bank of Cartersville for helping support this lecture series. Today we're talking about visitors from space, and we'll be talking about meteors and meteorites. And our speaker today is no stranger to TELUS. He's here often talking about rockets for our Build and Blast workshops, and he's here often helping us out with other astronomical things. And Chris Thompson is a NASA ambassador par excellence. He loves to teach about space. He loves to talk about all things cosmic, and so he is also. Are you still president or past president? Yeah, he is president of our local Meteorite Association, and so he'll be glad to answer questions about that if you want to join that merry band of meteorite hunters. So, without any further ado, let's give a big warm welcome to Chris Thompson.
Thank you, David. Appreciate it. How y'all doing today? Good. All right, we're going to talk about meteors and meteorites. I'm going to try to get around the stage because I like to actually see you guys more. My name is Chris Thompson. I'm a NASA Solar System Ambassador, and that is a program run by the Jet Propulsion Laboratory out of California that identifies citizen scientists or citizens who are interested in communicating the wonder of space to the general public. So thank you all for paying your taxes, because that's how we get here. So today we're going to talk about meteors and meteorites, and we'll start with how the solar system formed. So, a long, long time ago in a galaxy right here, the solar system began to form. It started out as a ball of gas and dust, and as it began to rotate, it flattened out, and then things began to come together. And as they came together, a star ignited in the center. And as that star ignited, it began to send energy out through that gas and dust and spread it out and allowed it to clump together. And so from that process, we got planets, we got minor planets, we got lots of cool stuff. So that's how it all started. It was this ball of gas and dust. So let's talk about our players for today. So here is an example of what our solar system looks like, and this is actually to scale for size. It's not to scale for distance. If you want to get an idea of distance, go on out and take a look at the solar system walk that TELUS has here, and it gives you a feel for how far apart things are up in space. But if we look way out at the edge are the Kuiper Belt objects. Pluto's out there. We've got our 8 planets, and all in their major moons. Mars, Earth and its moon, Venus, Mercury, and the Sun. Up here, we've got Ceres, which represents all the things in the main belt of asteroids. But what's missing in this kind of picture? What's missing in this kind of picture? This is why I built a comet. So we don't show the comets on the solar system because they're mainly ice and a little bit of rock. And to help illustrate that point, a little bit before we started, we built one. And this is a comet made of dry ice, water ice, and a little bit of paver sand to represent some of the solid material that goes into it. Now, this is just going to sit up here while we talk because we're going to refer back to it from time to time. But comets themselves, as Fred Whipple, the famous astronomer, put it, are dirty snowballs. It's ice with a little bit of rock attached to it. And they really can have very odd shapes. I mean, let's take a look at this. This is Comet Wild 2. Whoops, we'll get up here. Comet Wild. It looks like wild, but it's a German name. We have Comet Halley. Everybody knows Halley's comet. And this picture down here is actually Comet Halley. Then we have this one. Anybody pronounce that? Just call it Cherry Jerry. Okay, that's P67. That's Cherry Jerry. That is a contact binary. That's like 2 pieces that clump together. If you want to know what it looks like, just think rubber duck. And Hartley is another one. Odd shape to it. Small things generally have odd shapes. Big things generally have round shapes. Comets are out there in the solar system. They're really, really hard to spot. There's a whole bunch of them. If you have a really good telescope, you can do it. But there's going to be one this year that we've got a chance of seeing. And this is its track through the sky. And what I want you to focus on is there's a couple of constellations, Ophiuchus right here and Aquila. And this period between near the end of October and the early part of December is probably the best time for us to see this comet. It might be a naked eye comet. You might be able to see it without the aid of a telescope or binoculars. I say that might because these are notorious for disappointing us. I'll give you an example. The astronomers will predict what's called a light curve. And this is what we think the brightness is going to be over time. The brightness will increase as that object gets closer to the sun. And you can see the little vertical spike there, which shows you where it's going to be closest. It's kind of tracking along that way right now. But if it gets up in this area where it's maybe in the less than 6, let's say getting up to about 4 magnitude, we should be able to see it, especially if you're in a dark place. It might get to be magnitude 2, which is some of the stars that we see in the night sky. So we might get to see it. Don't come back to me later if you don't get to see it, okay? Because these are notorious for making our life hard. But that's one of the objects in the solar system. And for meteors and meteorites, comets are pretty important, particularly the meteor part. So, going back to our players, this is the base part of the solar system, but what is also near this object? This object is Ceres. It's one of the largest objects in the main belt. It's the largest object in the main belt of... Perfect. That's the largest object in the asteroid belt. So there's lots of other objects in the asteroid belt, but Ceres is the big one. So let's talk a little bit about asteroids. Asteroids come in all shapes and flavors and sizes. Here's 3 of them. Vesta, is number 4, so it's the 4th one discovered. It's the 2nd largest, and Vesta is about 325 miles across. Okay? We sent a mission to Vesta called Dawn and investigated that, learned a little bit about it, and actually found out that some of our meteorites come from Vesta. And we'll have some of those that you can look at a little bit later in our talk. The asteroid on the upper left is called Psyche. And NASA just sent a mission to Psyche. This is suspected to be an all-metal asteroid, one of the only ones we know that is an all-metal asteroid. And then there's one on the far right called Bennu. If you look at that one, this is tiny. This one's only 0.3 of a mile, 500 meters. This is a little one. And we just sent a spacecraft to Bennu. It was called OSIRIS-REx. And it sampled a piece of that asteroid and brought it back to Earth for us to study. So it's an amazing little trip. Now, most people think that those asteroids are everywhere. And when you look up in the sky, you can see a bunch of them. Here's just a few that we've had spacecraft fly past. Those spacecraft fly past, take pictures of them, and these are pictures to scale, so they're compared to Vesta. They look big, but when you put Vesta up there next to things like Ceres and the moon, you kind of get the perception that, hey, those aren't that big. They're big to us, but they're not big to space. If you were to combine all of those asteroids, even Ceres at 600 miles across, with Vesta and all of the other ones out there, you would get a mass of less than 10% of Earth's moon. So even though there's a lot of objects, there's not much to them. Now I'm about to dispel a myth here. We've all seen The Empire Strikes Back. We know what an asteroid field looks like. But I have to tell you that that's not an asteroid field. You want to see a picture of a real asteroid field? There you go. That's an asteroid field. Because the average distance between mile-wide asteroids is about 1 million kilometers. So there's a lot of space in space. I'm telling you, walk that solar system walk that Tellus has put in. It's a beautiful representation of how far apart things are up in space. Now, how do we know where all these things are? We take a look. In 2009, NEO, or WISE, was launched, and was later renamed NEOWISE, and its job was to survey the sky and find stuff for us. It's a planetary defense mission. It's science and research, but it's also to help us defend Earth. Now, NEOWISE is about to end its mission and will be replaced by NEO Surveyor in about 2028. And we'll continue to use a space-based platform to look for all these cool things in the sky. We've got lots of ground telescopes doing the same thing, so we're not going to be without protection. But we do have a new spacecraft getting ready to launch to help spot things in space. Now, we've talked about comets and asteroids. Let's talk about meteoroids. We're not going to spend very much time on this subject because meteoroids are just rocks in space. They're a little smaller than asteroids. There's really no accepted definition where that break is between asteroid and meteoroid. Just think they're little teeny tiny pieces. So small stuff we would call a meteoroid. But that small stuff plays an important role in what you guys will see on a yearly basis, and actually there's one coming up real soon. And those would be meteor showers. So annually we have meteor showers. In fact, there's a calendar that shows you every year those meteor showers come back, because a meteor shower is when the Earth's orbit passes through the trail left by a comet. There's one meteor shower that's actually from an asteroid, but we're not going to delve into that. Let's just go with we pass through the tail of a comet, and some of the debris that gets left behind by that comet is what creates a meteor shower. Now, why would there be debris left behind from a comet? That's why we built this. This is lots of ice, right? It's dry ice, water ice, and there's some rocky material put into it. As the sun heats up a comet and it sublimates the ices, the rocky material's left behind. And in space, that rocky material is going to stay in the same orbit it was in. It's just going to be free-floating rocky material. And as we pass through that trail of rocky material, we get plow right through it. Now, all of the little white dots are representing the dust and material that comes off the orbit of the comet. If you think about the orbit of the planets as being on this table, most of the comets are going to be kind of perpendicular to the table or at an angle. They don't really follow the same plane as all of the planets. Lots of them come from above or below the Earth, and so we just pass through one part of it. And that's what gives us these beautiful meteor showers. You look at a certain area of the sky because, again, it's a part of the trail that comet leaves behind. So as we pass through, it always comes from the same point in the sky. And that's how a meteor shower gets its name. It's whatever constellation those meteors seem to appear from. The Perseid Meteor Shower is going to take place. It's actually going on right now, but its peak is this weekend. Its peak is Sunday night. You can see meteors a few days before and after the peak. It doesn't have to be just that night. But go out, especially after midnight. I think Sunday is the first quarter, so we want to wait till the moon goes down, which will be around midnight, and then you'll have a chance to really see a beautiful dark sky and a chance to see several meteors. They'll all seem to appear from Perseus. They won't generally start exactly in Perseus, but if you trace them back, they'll all come back to that little spot in the middle there. Whoops, we're going to go to here, right from that point inside the constellation of Perseus, and that's how they get their name. Now, it's fun to go out and look, and you might see a few meteors an hour if you're fortunate in a dark sky spot, but every now and then, we go through a really densely populated segment of that trail. And there's lots of meteor dust that we're going to plow through. And when that happens, you get these. A meteor storm. And back in 1883, there was an enormous meteor storm, one of the biggest ever recorded. And people... You couldn't convince somebody just by talking to them what you had. So people created several different pieces of artwork to actually show this is what people saw across the United States. It was kind of like big news. It would have made social media if we had that in 1883. On the bottom right, there's a couple of photographs of a more recent meteor shower, the Geminids, and those are from 2022. So those are time exposures, not like what you would have seen, literally thousands of meteors per hour, hundreds per minute back in 1883. So that's a meteor shower. But what you need to understand about a meteor shower is they really don't leave meteorites. There's lots of stuff coming through the atmosphere, but it's basically dust. It's little tiny bits of matter that can cause a light in the sky as they pass through at tremendous velocities, 25,000 to 150,000 miles an hour. So they'll burn as they come through the atmosphere. They'll actually ionize the gas in the atmosphere and leave that streak of light, but then, poof, they're gone. What gets folks like our Meteorite Association excited is when there's a big enough object that comes through the atmosphere that it makes it to the ground. And those we call meteorites. Now, meteorites themselves come in lots of different flavors, and I'm going to go through the technical part of this kind of fast so we can take some questions. I see lots of hands coming up. We're going to take those at the end. Remember the story that back at the beginning, we started with this cloud of gas and dust. As that cloud congealed and created small objects that later grouped together into bigger and bigger things and ultimately ended up with planets, if those pieces never got stuck to anything else, they stayed small. And those small pieces represent the earliest solid objects we can find in our solar system. So planets, like our wonderful Earth, have geologic processes that change the material. We have erosion and volcanism, and we have different kinds of rocks that are formed by temperatures and pressures that are created by our planet. So that changes the rock. These early meteorites that formed through the aggregation of original chondrites, they never changed. So if we want to learn about the conditions of the early universe, we need to find the earliest rocks we can find, and those are meteorites. It's really cool that we get free delivery here on Earth. And it's like best Amazon Prime the universe can give us, is it drops rocks out of the heavens right onto the Earth. Now, if you're fortunate enough to find one, can identify it, you got something pretty special. But it coming through the atmosphere itself also changes those rocks. So that's why missions like Hayabusa, Stardust, OSIRIS-REx are important, because we're going out into the universe to find those rocks, catch them in their natural state, preserve them in that, protect them as they come back through the atmosphere, and then our scientists get to look at those original pieces of material that have not traveled through the heat and pressure of coming through an atmosphere. So that's even better, and we've learned a lot from the samples that OSIRIS-REx has brought back. So one way we see these are chondrites that are stone meteorites, and you'll see this is from a C-type asteroid. And that's our original early chondrites. You see the little balls of matter. I refer to them as interstellar dust bunnies. So if you ever had to do that work, you know what I'm talking about. Now, as those objects got bigger and bigger, as they gathered through gravitational or electrostatic force, they like collected bigger and bigger things, like a snowball running downhill. As that object gets bigger, and maybe around 20, 25 miles or so, if it has maybe some radioactive elements in it, it's going to generate heat. If it gets larger and has enough pressure from its gravitational, it's going to generate some heat. And as that heats up, eventually it's going to melt the interior. Now, if you've got all sorts of matter, rock, metal, all sorts of stuff, all melted together, eventually that melting is going to do what we call differentiate. And that's just a fancy word for the heaviest stuff sinks to the bottom. I talk about looking at a glass of chocolate milk. You ever mix up a glass of Hershey's Quick? Not a product endorsement. I can't do that. But if you took powder and you mixed it into milk and you have it there, it's all the same color. But if you leave it on the counter for a long time, it'll settle out, right? So all that powder kind of ends up at the bottom. That's what happens with a planetary body that's melted. The heaviest stuff sinks to the center. Tellus has a magnificent exhibit in the mineral gallery about the Earth, and it's peeled back, and you can see the center of it is this solid iron core. That's how we get them. A differentiated body. The heat melts it, and the heaviest stuff goes to the center of a ball. So the center of the ball gets the iron, and those meteorites that come from the center of that ball are where we get big iron meteorites. They're the center, and that's what we think Psyche is, the center of a destroyed planetoid. At the boundary layer between the rocky surface and the inner part, you're going to get rocks that are made not just of nickel iron, but they're going to be made of minerals along with that nickel and iron. And those are pretty cool looking too. Those are called pallasites, and those are stony iron. They're from S-type asteroids, and they are beautiful to look at. If they're cut thin and backlit, they look magnificent. It's God's stained glass windows. They're really cool to see. They make great jewelry, and sorry guys for sharing that with your spouse, because that's what ends up with my family. My girls all have pallasite jewelry. Those stony iron meteorites are suspected to come from the core mantle boundary where that stuff mixes together. And then the surface of those big bodies are where we get what are called achondrites. That's the crust. Earth's crust is really thin. So there's not a lot of these kind out there. They're a special kind of asteroid, a C-type. And those are cool because those ones are what we call planetaries. And they come from the surface. Achondrite meteorites come from places like Mars and Earth's moon. If you've ever looked up at the moon and you see craters, those craters come because stuff smacks into the moon. Take a look at the bottom right on the left-hand picture. You see that flash? That flash is a meteorite smacking into the moon at almost 60,000 kilometers an hour. Yeah, it's a big bang. A beach ball-sized meteorite smacked into the moon on the right-hand side picture and left a crater that's about 20 meters, 18 meters wide. That's a beach ball-sized rock that hit the moon and left that kind of a hole. Now, the moon doesn't have an atmosphere to slow it down, so it hits at the same velocity as traveling through space. Here on Earth, we're a little bit more protected. But those meteorites crash into the moon, and some of them are big enough to actually knock pieces off. And if they get away from the moon's gravity, pretty good chance they're going to come here. So we can get lunars and Martians on Earth through this mechanism, where a meteorite smacks into that parent body, knocks pieces off like a pool ball on a table, and brings it all the way to the Earth. Now, if you were to look inside one of those original meteorites, so this is not the planetaries, this is the original stone chondrites. If you were to look inside of those, on the surface they're going to be covered with this black fusion crust. But if you open it up, you see that it's still got the original building blocks from 4.5 billion years ago, and those have never changed. That's why scientists want to find a fresh fall, something that we see on a camera or it hits something. We know it's a meteorite, and we get it really quickly. It hasn't had much time to weather on the Earth. You'll see lots of meteorites that have been on the Earth for a long time, and they're quite rusted because that iron inside of them will oxidize with all the atmospheric water and oxygen that we have. So they'll change. But fresh ones, they look kind of like concrete. That's also why they're hard to discern from a regular Earth rock, because they do look so much like rocks that we see here on Earth. Now, there's a different kind of original meteorite too. This one's called a carbonaceous one. And this is what we found at Bennu. There's more carbon in these, and these are some of the oldest meteorites that are out there. In some cases, we've seen pieces of these meteorites that represent what are called pre-solar grains. If you can take that word and break it up a little bit. Pre means before, solar means the sun, and these are small grains. So these are things that were solid before the sun lit up. That's a long time ago. And we can find those kinds of things in rocks called carbonaceous chondrites. We'll have some examples at a table up here after the talk is over. If you were to look inside of those, you can see these things called calcium aluminum inclusions. These are materials that have a very high melting point, which means it takes a lot of heat to melt them. But reverse that. Think about a really hot cloud of gas that's beginning to cool off. The things with the highest melting point will solidify first. So that's how they become pre-solar grains. And they are not regular shapes in a carbonaceous chondrite. We have some examples, again, that you can see up close of what a calcium aluminum inclusion looks like. And you're looking at something that's older than the sun. Nickel iron meteorites are cool. They're all over the Earth. And they're the ones that kind of last the longest. They're the most solid material. So where stony ones or carbonaceous ones are going to weather pretty quickly, those big irons, they last a long time. If you haven't been to it, go to the Meteorite Gallery here. There's a large Campo del Cielo, which is a South American asteroid that fell, discovered about 1500. I think people in that area knew about it a long time before any Western explorers ever got there. But we've also got some examples of that up here as well. Those are big metal pieces that survive a long time, and they're pretty cool to see. On the outside, you see what it looks like. It has these regmaglyphs or thumbprints in it that are coming from the passage of that asteroid through the atmosphere. This is kind of what's left after it gets superheated. But inside is where you get to see what differentiates this kind of rock from anything that could be done on the Earth. People bring us metal meteorites. They're like, I got a big metal meteorite. This is really cool. It's a very quick test. You cut that and etch it with a solution that I'm not going to tell you about because I don't want hazmat coming to your house. And you see that pattern. This is called a Widmanstätten pattern, and it is unique to meteorites. You can't do this on Earth. This comes from cooling down a metal over a long period of time, and those crystals that form are definitive proof that the rock you're looking at is a meteorite. Earth rocks can't do this. And there's some really, really great examples of it. Another one I want to talk about briefly is the stony irons. Again, this is 3 parts to this picture. There's a backlit picture, a frontlit, and then a kind of both together. And that backlit picture tells you that cut thin, you can see right through those crystals. Anybody in here born in August? Born in August? Your birthstone is peridot? Well, if you're a gemologist, it's peridot. If you're a meteoriticist, it's olivine. That's an olivine crystal from space. Okay? It's the same kind of one we'd see here around a volcano, but this one came from outer space. Pretty cool. The achondrites, if you want to take a peek at what those look like, again, does this look like the stuff you got in your yard? It probably does. So some of these rocks, they look a lot like what you would see in an Earth rock, except these ones came from outer space. It's pretty cool. Now, a little bit of a table here. This is going to show. People always wonder, where does all these meteorites come from? If you were to look at what flies through the atmosphere, most of it is cometary, because this stuff, we're traveling through it all the time. About 95%. That never makes it to the ground. It lands on the Earth, but it's microscopic. There's about 40 tons of material every day. It's just microscopic. The Earth is a big place, and it's a wonderful vacuum cleaner for this part of the solar system. A little bit of that stuff that comes through is carbonaceous, and a lot less of it is the achondrites, either the irons or the stony irons. That's what comes through the atmosphere. But what do you suppose survives on the Earth? What we see, if we were watching for a dash cam, a lot of what we see are those ordinary chondrites, because that's a lot of what's out there. That's why they're called ordinary. But if you were to stumble across one out in a desert area or an ice sheet, what really survives are the irons. Those irons are we find a lot of those because they survive longer than the other rocks do. So they're more likely to stay available to be discovered than a chondrite does. Now, you might be asking the question is Earth the only place we can find a meteorite? That's a leading question, right? So what's the answer? We've had spacecraft on Mars that have discovered meteorites on the surface of Mars. And honestly, think about this. The Apollo astronauts traveled to the moon from 1969 to 1972. They brought back samples. And just recently, in one of those samples, the researchers found a piece of crystal that actually came from the Earth. So we've brought back to Earth a piece of the Earth that got blasted off millions or billions of years ago and returned it to the Earth. So we've got a Earth meteorite from the moon that we brought back to the Earth. Right? Amazing, huh? Now, what happens when those rocks hit the Earth? Some of them leave a hole. Most of them aren't going to leave. The little ones don't leave a hole, but the really big ones, they leave impact craters. And the one out in Arizona, Beringer Crater, is about 1 kilometer across, and it was made almost 50,000 years ago. Now, that was a pretty good-sized rock that hit, but you see the one on the bottom there, Chicxulub? This is the one where the dinosaurs looked up one day and said, uh-oh. That was 6 miles wide, which means at the point when one end hit the water, the other end was still higher than where airliners fly. That's a big rock. That one left a big hole down in the Yucatan Peninsula, off the Yucatan Peninsula. But there are some really well-preserved meteor craters on the Earth, and those we see all over. Those, as you can imagine, inside of those are altered pieces of our planet. So it's not the meteorite itself, but it's what happened to the Earth when that gigantic rock smacked into us. And we get these kinds of materials, and again, some examples of it over here so that you can look and see them up close, including pieces of the Sudbury impact area from up in Canada. Another really cool one, and we've got an expert on tektites sitting back there who's going to be embarrassed I'm pointing him out, but Sean's really our expert on tektites. And these are pieces of Earth's sand that melted through an impact event. Either a comet that came in and airburst detonated and heated up the area, or an impact that created enough heat to melt the Earth. And if you've melted sand, what do you get when you melt sand? Glass. If you're out in the desert and you got nothing else in there but sand, you get these beautiful examples of Libyan desert glass, and they can be clear or milky white or a little bit yellow, but those are there. If you're in an area that's got lots of jungles and water and stuff that lives in those things, they are going to have a lot more impurities in them, and they might be black. If you're in Europe and you've got different kinds of minerals, you might get green, and that's called moldavite. We've got examples of that all in the case in the back in the meteorite gallery. Now, if you found something cool like that out in the Libyan desert and you wanted to impress King Tut, you'd probably take a piece of it and do some artwork, right? So this is your art project. Take a piece of Libyan desert glass and carve it into a scarab beetle and put it into this cool thing. And then get it there with King Tut. That's a real piece of jewelry from King Tut's time. He also even had a knife made out of meteorite material. So these things have been around for a long time that we've known about. These tektites and meteorites fall all over the world. The black dots are where meteorites are found. The little colored splotches are where tektites are found. And you'll notice that one of those spots is right here in Georgia. Now, it's really, really hard. The tektites from Georgia are very rare, very precious, but they're here. Those things came from a crater that formed in the Chesapeake Bay 35 million years ago. So think about it. The force that it would have taken to eject something from Maryland that landed in Georgia, and we can find it today. Pretty cool. Now, Tellus has a long history of having exhibits around meteorites, and I want to show you a couple of them right here. That car on the left is the Peekskill car. Now, when that meteorite fell, I think it was a Friday night, and there was lots of folks out there with cameras watching their kids play football, and there was a fireball that came across the sky. So lots of people got pictures of this. But the meteorite itself hit this lady's car and went clean through the trunk. So that car is pretty special. The meteorite's special, and the car is special, and that car were on display here at the Tellus Museum a couple years ago. And on the right is a guy named Hal Povenmire. He's examining a meteorite that fell in the Georgia town of Claxton and hit that mailbox. And that's a pretty famous meteorite fall as well. But the most famous, the most important for Tellus has to be this one. Y'all seen that? I mean, think of it. The Earth is a big place. Tellus Museum's a really special place. But how cool is it that we had a rock drop right here in town? Went through the roof, bounced off a few rafters, went through the wall, banged off a door, and that meteorite still has all those marks on it right now, and it's displayed in that little case. So y'all want to take a look at that every time you come to this museum and appreciate that we've got a meteorite that traveled from the beginning of the solar system and is sitting right here on display for you at the Tellus Science Museum. All right? David, we got time for a couple of questions?
Yes, we do. If you have a question, raise your hand. I'll come over with a microphone. Since we're recording this, we want to get your on recording. So I'm going to come over here to the first question right here.
So, was the OSIRIS-REx mission the one that they couldn't open the thing for the meteorite sample?
Yes, so when the meteorite sample return capsule got back to Earth, they took that to Houston and had it in its special cases. They went to open it all up. They got almost all of the bolts undone, but they couldn't get the last couple done. They couldn't get the last couple open. So they went into what's called Plan B. Right? You have a primary plan, and you have a backup plan. So they actually created some new instruments. They were very careful about how they created them so they wouldn't damage they had to make sure that it was made of materials that could go in that case so it wouldn't alter the meteorites. It had to fit inside the case. The technicians had to be able to manipulate it, and it had to make sure that it didn't damage anything that was inside. They figured that out. They got the whole thing open. They got all the samples out and have done wonderful science as a result of that. So the lesson there is have a plan, think through everything you can think of, but be ready to alter the plan when something unexpected happens. Don't give up. We were talking about this earlier. You've never lost unless you give up. So you can solve that problem.
Got another question over here.
Have you ever been to space before?
My family thinks I'm in space right now. But no, I have not been to space. I do have a history of doing some work with NASA, and I also went on what's called a zero-G flight, so it's a parabola flight, and I got to experience weightlessness a few times, and that was really, really fun. But that's something that you have to be ready and willing to go through an experience like that. I highly recommend it, but I can't seem to talk anybody else into it. It's like jumping out of an airplane. Some people do it, some people just won't.
All right.
What was the meteor's name that hit the woman's car?
The meteorite's name that hit the woman's car, it was called Peekskill. So meteorites get named for the location where they hit. So we have a Cartersville meteorite here because the city it hit in is Cartersville. The ones that landed out there in Arizona, those are named Canyon Diablo because that's where it's a place, a post office very close to where that hit. The only ones that really don't get names are places that are so uninhabited there's no place name to do it. And there we say they're some part of Africa, like Northwest Africa, and we give them a number. But most of the time they're going to get a name of the place. So if you have a meteorite that you think like hit your house or hit your car or something, don't get rid of any of that stuff, and make sure you get it reported into the American Meteorite Society or one of the folks here at MAG, because you're going to be famous. Okay?
Okay. Got a question over here.
What is the most common type of metal found in meteorites?
What's the most common type of metal found in meteorites? That would be iron. So almost all the metal that we see in meteorites is iron, with a little bit of nickel and an itty-bitty tiny bit of almost everything else.
Let's have a big hand for our speaker. Thank you, Chris. We have a great set of activities for all my young meteorite hunters out there over here in this corner of our banquet room, and my staff's getting over there getting ready to help you with some activities.